Hey everyone, welcome to the video. This is part 2 of the median of two sorted arrays problem, where we will finally be explaining the O log m plus log n solution. So let's get started. Let's quickly recap where we stopped in the last video. We defined the pivot of an array as the index that is in the middle of the array. For example, pivot A and pivot B are marked in the diagram here. We mentioned that there were too many factors affecting how to find the median. For example, is k considered big or small compared to the length of the array? For example, is k equals 1, 2, 3, or is k near the end of the sorted array? Also, the decision of where we find the median depends on the relative value of the pivot elements in both arrays, and our understanding of the input would change depending on if the value of A's pivot is greater or smaller than B's pivot. Using that intuition, we defined 4 scenarios for the problem. The first is if pivot of A plus pivot of B is greater than k, or simply stated, the number of elements in the first half of A and B combined is greater than k. This would signify that k is relatively small compared to the length of A and B. The next subscenario is the value of A's pivot is at most B's pivot value. The second scenario happens when, again, pivot of A plus pivot of B is greater than k, but A's pivot value is greater than B's pivot value. The third scenario happens when pivot of A plus pivot of B is at most k, signifying that k's value is too big and near the end of the sorted array. And the next sub-scenarios are again the relative values of A's and B's pivots. This is great. Now we divided the problem into multiple scenarios. Let's consider one scenario at a time and try to solve them. The first scenario happens when pivot of A plus pivot of B is greater than k, and the value of A's pivot is at most B's pivot. Let's make that more concrete. Let's set A's pivot value to 3 and B's pivot value to 5, and k equals 3. Observe that pivot of A plus pivot of B is just simply 2 plus 2, which is equal to 4, and 4 is greater than k, which is 3 in this case. Similarly, the value of A's pivot is at most the value of B's pivot. Now, let's ask ourselves, where can the third smallest element of the sorted array be? Can it be in the first half of A? Take a few minutes and think of an input that completes A and B above, that ensures the third smallest value is in the first half of A. Now, I'm sure if you spend enough time, you can come up with an input like this. Here's the sorted array order, and the third smallest value in the sorted array is 3, and 3 is in the first half of A. So it is possible that the third smallest value is in the first half of A. What about the second half of A? Take a minute and again think, is it possible to have the third smallest element in the second half of A? I'm sure if you spend enough time, you can come up with an input that looks like this. Here's the sorted array order, and the third smallest element happens to be 4, and 4 is in the second half of A. So it is possible that the third smallest value is in the second half of A. What about the first half of B? Again, take a minute and think. Is it possible to have the third smallest element in the first half of B? I'm sure if you spend enough time, you can come up with an input that looks like this. Here's the sorted array order, and the third smallest value in the sorted array is 4, and 4 is in the first half of B. So it is possible that the third smallest value is in the first half of B. However, you have to be a bit careful, because it is impossible that the pivot of B is the third smallest element, since it's already at least larger than 3 elements. What about the last half of b? Now, be careful here and try to come up with an example where the third smallest element is in the second half of b, or prove that it's impossible. I'm sure if you spend enough time, you would notice that it's impossible. Any element at or after b's pivot cannot be the third smallest value, because there are already at least k elements that are at most the value of b's pivot. So no element at or after pivot b can be the kth smallest element themselves. Let's summarize this. For the first scenario, the kth smallest value can be in the first half of A, the second half of A, the first half of B not including b's pivot, or the second half of B. So we can simply delete the elements starting from b's pivot until the end of B and search for the kth smallest value in the remaining arrays, since we just proved that it's impossible that the kth smallest value is in the second half of B. Great! Now let's try to do the same analysis but for scenario 2. Namely, if pivot of A plus pivot of B is less than or equal to k, and the value of A's pivot is at most B's pivot. Let's take a more concrete example with A's pivot being 3, B's pivot being 5 again, but this time k being 5. You can verify that this example satisfies the scenario constraints. Now, where could we find the fifth smallest element in this input? Can we find the fifth smallest element in the first half of A? If you think for a few minutes, I'm sure you'll see that it's impossible. Any element of A is bigger than at most pivot of A plus pivot of B elements, which is at most k in this case. So it's impossible that any element in the first half to be greater than k elements, since there are simply not enough elements in the first half of A and B combined. What about the second half of A? Again, playing around with the input, you can come up with this input. The fifth smallest value is 4, which is in the second half of A. So it is possible that the fifth smallest value is in the second half of A. What about the first half of B? Again, playing around with the input, you could come up with this input. The fifth smallest value is 5, which is in the first half of B. So it is possible that the kth smallest element is in the first half of B. Finally, what about the second half of B? Again, playing around with the input, you could come up with this input. The fifth smallest value is 7, which is in the second half of B. So it is possible that the kth smallest element is in the second half of B. Alright, let's summarize this. For scenario 2, the kth smallest value can be in the second half of A and all of B, but not in the first half of A. So we can safely delete the first half of A. However, we have to be careful here. We won't be searching for the kth smallest value in this new input. Instead, we're searching for the k minus pivot of A element, since we deleted pivot of A elements from the original input, so we shifted the kth smallest value to be now the k minus pivot of A element in the new input. Now, if you do this tedious analysis for every one of the last two scenarios, you get the following conclusion for the 4 scenarios. Notice that in each scenario, we're able to delete half of one of the two arrays and search for the kth, or k minus pivot of A, or k minus pivot of B element in the new smaller input. But we already know that this search is exactly the function we're trying to think of. This should immediately imply recursion. Each of the searches can simply be implemented recursively on the smaller input as shown in yellow for the 4 scenarios. However, there's still a small problem that I've been leaving out till the end. How do we delete half the arrays efficiently? One way we can do is to copy the entire array. For example, if you want to delete the first half of A, we create a new array, A prime, of half the length of A, and copy the second half of A into A prime. However, this would be problematic because we would have to do a linear loop again, which we already said was too slow. An alternative trick we can do is to instead modify the recursion definition of the function we're writing to include the boundaries of A and B that we're currently considering. So the function signature changes from this to this, simply adding L1, R1, L2, and R2 to the arguments of the function. This means we are restricting A from index L1 to index R1, and B from index L2 to R2. Alright, now let's rewrite the recursive calls we discussed earlier in terms of this new signature. Here's how to do it. Notice in the last two scenarios that instead of subtracting pivot of A or pivot of B, we're deleting the number of elements from the left pointer to the pivot element which is at the middle of the array. Take a few minutes to digest the recursive definition. We're now finally ready to write the code for get kth element in sorted order function. First, we will check if L1 is greater than R1. If that is the case, then that simply means that A is empty. So the kth smallest value in B from L2 to R2 is simply B L2 plus K. Similarly, we can check if B is empty and return the kth element in A from L1 to R2. Next, we calculate M1 and M2, the indices of the pivot elements of A and B from L1 to R1 and L2 to R2 respectively. If the value of A's pivot is smaller than the value of B's pivot, and the number of element in A and B's left side is greater than K, then we delete the second half of B and recursively call get kth element in sorted order with arguments A, B, K, L1, R1, L2, and M2 minus 1. If, on the other hand, the number of elements in A and B's left side is smaller than K, then we delete the first half of A and recursively return the function shown. On the other hand, if the value of B's pivot is smaller, then we will do a small trick where we will recursively calculate the kth element, but with A and B's order reversed in the arguments. This will ensure that in the next recursive call, their values are reversed and they would enter the first part of the if statement that we just discussed. Note that you don't really have to do this, and you can code the two subcases as we did for the first if branch. But honestly, making sure the indices are correct in this problem is an absolute nightmare, and this is an easy way to simply simplify your cases from 4 to 2, which also means you're debugging 2 cases instead of 4. And this is it. This very short but extremely elegant function returns the kth smallest value in the sorted order of A and B. To call the function, we simply call it on A, B, K and set L1 to 0, R1 to the length of A minus 1, L2 to 0, and R2 to the length of B minus 1. To calculate the median, we remember from the first video that the median is simply the middle element if the length of A plus B is odd, or the average of the two middle elements if the length is even. This code handles both cases and does 2 calls to the function we just implemented for getting the kth element. As for the time complexity, each time we either cut A in half or cut B in half. In total, A and B have M and N elements respectively. So the recursion can continue cutting A for at most O log M iterations, and cutting b for at most O log n iterations. So the depth of the recursion is at most O log m plus log n. In each level, we only peek at the middle elements of A and B, and do other O1 calculations. So each level of the recursion does O of 1 work. This means that the algorithm really only needs O log m plus log n time and space. Thank you for watching the video. If you liked it, please feel free to like the video and subscribe to the channel. This really helps me a lot. And until the next video, I'll see you soon.